Okay, thinking about motor, descending tracts, and somatosensory ascending tracts. Okay, that's where we're going to start today. And whenever we start a new section, I like to do a big overview, a big general overview. So just like looking down at large topics. I mean, everything we're going to cover when we're talking about spinal cord, and just kind of go back through that. This is my section right here. What kind of section is this? Sagittal. Okay. For the ease of presentation, I'm choosing that this would be like the left side of my brain, and the split would be here. But this, what's this represent? Does anybody? Yeah, that's the central sulcus. Realize you won't see the central sulcus on a sagittal view ordinarily, but to just make things clear, I'm putting it in there. So really it would be on the outside, right? But for right now, I'm just going to label that my central sulcus. Okay. So this would be the cortical region. What's this structure here? That's my thalamus. Okay, and then going down, looking at parts of the brain stem. The uppermost part is midbrain. And then this guy, pons. And then this one, medulla. Okay, just basic sections, putting everybody in the same place. And then this down here is going to be my spinal cord. Okay, and this guy back here, does anybody remember? Cerebellum, you got it. Coordination and balance. Okay, thinking about, like I said, this is just going to be a great big overview of all the different tracts. Okay, we're talking about motor is descending tracts and somatosensory is ascending tracts. When I say the word tract, what does that mean? Sorry? White matter. Yes, good job. Yeah, myelinated axons. That's going to be my white matter. That's just another word for myelinated axons. All these things that are called tracts that I'm going to label here and just kind of get a general feel for, that just means that these are all myelinated axons that start in one place and finish in another place. And they're all traveling together. Okay, and we'll talk about nomenclature here. So let's start with general somatosensory information. So as we talked about before, you have general somatosensory information. That's information coming from the environment. So this is my dendrite is going to be there. It's coming from the outside and then going up. So this is just general somatosensory. And somatosensory, again, is just information that's coming from the body. Sensory information coming from the body. We talked previously about two different tracts that were responsible for carrying somatosensory information up to the central nervous system. Does anybody remember those? It's been a while. Well, we talked about it a long time ago. One's going to be the spinothalamic tract, or STT. Okay, STT is spinothalamic tract. Okay, and the other one is DCML, and that's your dorsal column medial lemniscus. Dorsal column medial lemniscus. We're going to talk about those in a lot more detail. Again, this is just the big overview. No real detail here. So, somatosensory information perceived by these dendrites comes into the spinal cord and heads on up to synapse in the thalamus. Okay, for right now we're just putting all this in one neuron. Okay, so it's just the overall pathway. Okay, once we get into the thalamus, then that information is going to come up, and does it go to the central gyrus or the post-central gyrus? Post, yep. So those axons that are put out here are going to supply information to the post-central gyrus. Okay, so general somatosensory information just comes in from the environment, goes into the spinal cord, it's all the way up, synapses in the thalamus, all somatosensory information except for olfaction, sense of smell, synapses in the thalamus. And that information is then relayed to the post-central gyrus, which is the somatosensory cortex. Okay, pretty easy, right? Now, that's going to be, and I'm going to choose to represent the sensory information in either a blue or a green going forward. As long as you keep consistent colors throughout, I think it might make it easier. So thinking about, there's another tract that we haven't really talked about before. And this tract is going to be responsible for conveying information mainly from your joints. Okay, it's going to convey information that's responsible for non-conscious proprioception. Okay, the name, there's two different tracks. We're going to talk about both of them, but we're going to group them here together. And these are called the spinocerebellar tracks. Okay, spinocerebellar tracts. And there's going to be a dorsal and a ventral, just two of them that we're going to talk about. And they're going to be responsible for non-conscious proprioception. We'll talk a whole lot more about what they do and what they carry when we get to the cerebellar portion of the course. But for now, we're going to look at where they reside in the spinal cord. And I said that these tracts all have a common origin and a common destination. So if this tract comes in to the spinal cord, that's the spino part, where do you think it ends at? Cerebellum. That's it. Just that easy. So it comes in and then provides information to the cerebellum. Paperclip. Okay, and those are your spinocerebellar tracts, responsible for non-conscious proprioception. Where conscious proprioception is going to be carried by the DCML. And we'll talk about that as time goes on. Questions? Common origin, common termination. All these tracks kind of travel together. Okay, as far as your sensory information, so you have your non-conscious proprioception and all your somatosensory information coming in. That's it. Two different, well, really, DCML, STT, and spinocerebellar, dorsal, and ventral. That's it. Those are your ascending tracts because they start here and then go up. It's interesting to think about the spinocerebellar tracts as being non-conscious or unconscious. You're not aware of it because it never really makes it up to the level of the cortex, right? Your cortex is responsible for that consciousness, your conscious awareness. Spinocerebellar comes into your spinal cord, goes right to your cerebellum. Never makes it up to where you can be aware of something. Okay, we have. Moving on to motor. Motor is going to be like a reddish, orange, pinkish. Yes, Sam? Yeah, better write that down. We'll get to more of it, but I should probably write everything down. So this is going to be, it carries non-conscious proprioception. Okay, non-conscious proprioception. And what that means is that I am not really aware of this information. All this information is coming from every joint in my body. And it's just being automatically relayed to the spinal cord, to the cerebellum continuously throughout all movement. Okay, it's that important. Yes, Tyler?
Is the level that you're drawing, is that Tyler?
No, I'm just trying to fit everything in there. It might get a little crowded, so I'm trying to leave some space. As long as you have different colors, you should be able to discern where things are. talk about levels later. Any other questions? Some make sense for where we are right now? So all these different spinal levels, you're going to have your spinal cerebellar tracts and your somatosensory. This is intended to be just a great big overview, looking at how things come in, where they go, essentially, and what's there, really. Eventually, as we go through the rest of the talk, we're going to draw a section through the spinal cord, and we're going to look at where all these tracts reside. Like I said, all the tracts kind of clump together in different areas. That's what they're there for, travel together. Okay, let's think about the motor now. Motor are going to be the descending tracts, and as far as the descending tracts are concerned, we have the big one up here. It's going to come out of the primary motor cortex, which is the precentral gyrus, right? So here I'm representing a neuronal cell body. Here's my neuronal cell body. Okay, that's the neuronal cell body. That's going to be a multipolar neuron starting out in the premotor cortex. Going to have a lot of motor information. The motor information comes down here. So this is the neuronal cell body. Here's the axon coming down. The axon's going to come all the way down, travel through the brainstem, through the spinal cord, and then come out. Okay, and this is going to innervate skeletal muscle. It's going to be your basic skeletal muscle, and that's going to travel through this axon. This group of axons coming down has a name. It's a specific tract. Does anyone know the name of the tract? So let's say it goes from the cortical region to the spinal cord. What do you think it might be called? That's your corticospinal tract, exactly. Corticospinal tract. Just that simple. Okay, I'm making it real easy to see here by just drawing one tract and one neuron, but realize there's thousands all traveling together on both sides. Okay, now we have next one. Let's talk about, let's see that color. Let's do this one in sort of a maroonish. There's a great big old nucleus that lives in the midbrain. We use it as a landmark for lots of different things. Okay. That's kind of a maroonish color right there. So we have this great big old nucleus lives in the midbrain. Okay. This nucleus is called the red nucleus. So the red nucleus, just neuronal cell bodies, create a tract by sending out axons. These axons travel down the spinal cord. Okay, and the name of this tract is called the rubro for red. Rubro, B-R-O, spinal tract. R-U-B-R-O, rubrospinal tract. And the rubrospinal tract carries information about, specifically in humans, upper extremity flexion. Okay, so it carries upper extremity flexor information. Okay, this this will be important as you go through to neuro rehab as a clinical presentation. If somebody is in a coma, if the problem is above the level of the red nucleus, that means the red nucleus is still working. There's a lesion up here somewhere. They might present like this. This is called decorticate rigidity. You can see my elbows are bent, right? Now, if the lesion is below the level of the red nucleus, that means this tract is gone. They present with decerebrate rigidity. Upper extremities no longer flex. My wrists are flexed, but my elbows are straight. Two different clinical presentations you'll talk about next year a whole lot. But that's the importance of the red nucleus. In humans, it promotes upper extremity flexion. And you can see that in patients post-brain injury. Questions? Okay, moving on down the chain. So we're here in the midbrain. Let's move down to the pons. And in the pons, we have the nucleus. We're going to see all these nuclei when we get to the brainstem portion of the course. I like to represent this as a kite-looking thing. Okay, it's just 4 quadrants to it. And this is your vestibular nucleus. Vestibular. So it's going to be the one responsible for obtaining information from your vestibular apparatus in your inner ear. Part of cranial nerve number 8 comes into part vestibular, part cochlear, but this is your vestibular nucleus. And does anybody know the function of the vestibular system? Not proprioception. Close. I don't know who said that. But did you say something, Jared? Balance, yeah. So it's going to be involved in balance, and specifically, the vestibular system is involved in telling your brain where your head is in 3-dimensional space. Okay? Are you sitting upright against gravity? Are you turning your head side to side? That's the vestibular system's job, and we'll talk about how it does that when we get to that portion of the course. But in general, this is a very handy track that I like to use clinically quite a bit because I know that if I put somebody upright against gravity, I'm activating their vestibular tract, and what happens there is that vestibular tract is going to send out axons that travel down the spinal cord and come out. And if you're upright against gravity, which muscles do you want firing? You want your flexors or extensors firing? What do you think? Extensors. Yes, I want my extensors firing. I want my hip and knee extensors and my back extensors, cervical extensors, all firing if I'm upright against gravity. So this is the vestibular nucleus. Coming out of the vestibular nucleus, there are axons traveling down. And then this is the, believe it or not, vestibulospinal tract. The vestibulospinal tract stimulates extensor musculature to fire. So I know that if I get somebody upright against gravity, as opposed to lying down, that I'm going to start promoting extensor muscle contraction, and that's going to help them function. They're going to be upright against gravity. They're going to be able to tolerate it. Okay, moving on down. Let's make this, hopefully this comes through. Now down here in the medulla, there are a diffuse body of nuclei. Okay, I'll just put them over here. Kind of represent it like a long thing. It's just a diffuse body of nuclei that reside in the medulla. Okay, this diffuse body of nuclei has a name. I'll just label it with black. These are known as your reticular formation. Just a lot of words today. Your reticular formation, it's nothing more than a diffuse body of nuclei. Nuclei are just a collection of cell bodies in the CNS, right? Neural cell bodies. And this reticular formation is responsible for awareness, awakeness, alertness. So if you're having trouble with your reticular formation, it's kind of like a light switch that says you're awake or not awake. Right? So if you're asleep, your reticular formation shuts your brain down. Does anybody here sleepwalk? No? I sleepwalk. So, kind of scary. Yeah, so what happens is your reticular formation has got your brain shut down, you're asleep, but you're still motorically active. Right, so that's an example. Reticular formation is, shut your brain down. So if you sleepwalk, you are not aware of what you are doing. Even if you talk in your sleep, you are not aware of anything that you're saying. My husband has had lots of fun with this one, let me tell you. But he can talk to me, and I'll be arguing that the benevolent plant in the corner needs water, and he's like, there ain't nothing up there. I'm not aware of that. Right, but that's because my reticular formation is shut down, my brain, but everything else is still working. Okay, reticular formation, diffuse nuclei send down axons down the spinal cord here. Anybody, any guesses as to what that tract is going to be called? Or yeah, reticulospinal tract. That's your reticulospinal tract. And again, if you think about it, when you're awake or aware, you want your extensors to be firing. If you're not aware and you're asleep, chances are good you're going to be supine, right? But when you get up, you want your extensors to be firing. So this is going to help fire extensor musculature. Lots of new words. Hopefully we can make sense of these. And again, this is a great big overview. These are all the tracts, both somatosensory or sensory tracts, as well as the motor tracts, all the different motor tracts that we're going to be looking at throughout the next few days. Did you have a question, Pat?
Yeah. I was just going to ask what individually do the reticulospinal tract and the vestibulospinal tract do in the sense of musculature? Are they work on separate parts of the body or
So both tracts will cause the musculature, extensor musculature to fire, especially the extensor musculature that you need to be upright against gravity. So don't think so much upper extremity as much as thoracic and lumbar and hip needing extensors just so that you're firing and able to stand upright against gravity. The difference between the two of them is that the vestibulospinal tract fires even in a person who's in a coma. So if somebody's in something called a vegetative state or an unconscious state, I can use the vestibulospinal tract. Where their reticular formation might not be active, I don't need that as much. But if a person is active, awake, aware, then both tracts will be working simultaneously. So one requires consciousness or awareness, the other just requires upright against gravity. Does that make sense?
Yeah.
Marty, did you have a question? Okay, great. Any other questions? Does that make sense to you?
Yeah. Is it the vestibulospinal that operates even when?
Okay. Yeah. And you can think about that. If the reticulospinal tract it needs consciousness or awareness, the vestibulospinal tract just works, no matter what. So I can use it in a patient in a coma and get their muscles to fire. Any other questions? That makes sense. And again, this is a great big overview. We are going into much, much more detail than this. Okay, and we've got 3 class periods to do it. This is just everything we're going to cover. Everybody good? Yes? Okay. Let's go ahead and move on then. So, the next one's going to be your motor. This one's going to be your motor and descending tracts from the front. I tried to make it, so looking at this picture. I think seeing it from the side is a little bit easier because I can just represent going from the outside environment up to the CNS or from the CNS out to the musculature. Okay, looking at it from the front, we're going to start to see that things cross over or decusate. at different places, depending on which track we're looking at. Okay? Decusation, what does that mean? Does anybody know? It means just simply crossing over, and what decusates, or decusation, kind of like the corpus callosum, how you cross over from one side to the other. That's a great big old decusation. Okay, nothing more than white matter tracks. Okay, all right, let's start with, okay, so this is going to be frontal section, something we've seen before. Okay, again, motor is going to be descending, somatosensory ascending, and I'll try and keep my colors fairly simple. And just for ease of presentation, I'm going to choose to put dots down here through the middle of my frontal section. So coming through the cortex, in between the thalamus, right down the midbrain, through the pons, the medulla, and the spinal cord. Okay? If I do that, then I think it's going to be easier for you to see where things cross over. Let's start with the STT, or the spinothalamic tract. Your STT, spinothalamic tract. Now I'm going to start to talk about what these things carry. Does anybody remember what the spinothalamic tract carries? What kind of information does it receive from the environment and bring up to your CNS? What kind? Which ones? What's somatosensory? So I heard crude touch. So let's start with, so spinothalamic has crude touch. What else? Pain, good. And temperature, okay? And you can think of the spinothalamic tract, think of crude touch, pain as temperature being really, really primitive senses, right? Those are your most basic sense. So it's a really primitive tract. Okay, spinothalamic tract, and we talked a little bit about the neuronal cell body being a pseudo-unipolar neuron. So let's go ahead and draw our pseudo-unipolar. And this neuronal cell body here is going to exist in the dorsal root ganglia. We can't see that yet, but we will see it eventually. So here's my neuronal cell body for my spinothalamic tract, okay? Little stalk. And then the dendrites are here, and they're going to be responsible for carrying this information into the central nervous system. With the spinothalamic tract, it comes in to the spinal cord on one side. Stays on its same side. Okay. Once it comes in to the spinal cord, the axon is going to synapse with a neuronal cell body on the same side of the spinal cord. And then that neuronal cell body sends out an axon that decusates. That means it just crosses over to the opposite side. And then once it's decusated, travels all the way up to the thalamus. Synapses with another neuronal cell body. And then this neuronal cell body sends out an axon sending information to the somatosensory cortex. Lots of information here. I don't know if you remember, I think it was a couple of classes ago that I was talking about somatosensory information coming in from the environment is a 3-neuron system, right? So we can label those. This first neuron here is called your first order neuron. It's first in line. It's your first order neuron. Okay, your first order neuron for the spinothalamic tract comes into the spinal cord, synapses with your second order neuron here on the same side. And then, as you're going to find out, for the somatosensory systems, anyway, it's going to be your second order neuron that decussates. So just coming over here to the opposite side, that's called decussation, D-E-C-U-S-S-A-T-I-O-N. That's decussation. It's always going to be your second order neuron that decussates in your somatosensory systems. Okay, and then moving on up here, located in the thalamus, you're going to have, so here's your second order neuron, and then you have your third order neuron in the thalamus. So there's your 3 neuron system. So it just takes 3 neurons to convey information from the environment all the way up to your CNS. We talked about that a little bit the other day. Okay, and it's going up here. Let's label this the somatosensory cortex or postcentral gyrus. All the same. Questions? You see that? 3 neuron system. So this first order neuron here, this neuronal cell body, resides in the dorsal root ganglia. Talk about that more later. It's going to synapse on the same side to the second order neuron. Second order neuron sends out an axon that decussates, goes to the opposite side, travels all the way up through the spinal cord, through the medulla, pons, and midbrain, all the way up to the thalamus. That synapses with the third order neuron located in the thalamus, and that thalamus sends out an axon to communicate information to the somatosensory cortex. And that information that's communicated is specifically crude touch, pain, and temperature. Very primitive sense. Got it? Yes? No questions? Okay. And that's going to be a little bit different. Oh, another important thing to think about when you look at these pathways, you're going to be able to see that I talked previously before that the right side of the brain, this would be the right side, is controlling information coming from the left side of the body. That's how that happens. Everything crossed over. Okay, for cortical senses, that's going to be true. Okay, we can label this. This would be the right side, right? Because this is the back, because it's cerebellar, and then this would be the left side. Yes, hopefully make it a little bit more clear. Okay, so sticking with my color system, if I can use this one. Now let's talk about the dorsal column medial lemniscus. So, same situation here for the dorsal column medium lemniscus. I have my neuronal cell body that's sitting in the dorsal root ganglia, and I have my little stalk, and then I have my dendrites sticking out here. And this is going to be DCML, dorsal column medial lemniscus. So I'll write that out now. Okay, so DCML stands for dorsal column medial LEMNISCUS, dorsal column medial lemniscus. Believe it or not, these words are going to be so common to you by the end of the semester. It's ridiculous. I know they're like Greek right now. But DCML is something, and STT is going to be something you're very familiar with. Does anybody remember what kind of information DCML conveys to the CNS? Yeah, fine touch, good. Fine touch, what was the other one? Anybody? Vibration, yep. One more. Conscious proprioception. This is going to be conscious. I'll put proprioception, but this is the conscious proprioception. Conscious proprioception. That just means that I'm aware of it. Okay, an example of that would be if I'm working with a patient and I want to test their proprioception ability, I might ask them to close their eyes, and then I might move the tip of their finger either down or up, and they just need to tell me which way it's going, down or up. Okay, that's proprioception. But they're very much aware of where that finger is moving. Whereas if somebody's just running, they're not aware of where their knee joint or ankle joint is in three-dimensional space at all times. That's the job of the cerebellum. That's going to be the non-conscious or unconscious proprioception. Okay? You seen that one before, Sam?
Sorry?
Have you seen that one before? You have? Okay, that's going to be your proprioception. Okay. Now, DCML, a little bit different system. What happens is the neuronal cell body is here in the dorsal root ganglia. There's an axon that comes in, and instead of synapsing right away in the spinal cord like the STT did, what's going to happen is it's going to travel up to the level of the medulla, and that's where it's going to synapse. Okay, so labeling this for the DCML, this is the first order neuron. Okay, your first order neuron doesn't synapse right away, the spinal cord. It stays on the same side of the spinal cord all the way up to the level of the medulla. Okay, then when it gets to the level of the medulla, it synapses with this second order neuron. And once it synapses with the second order neuron in the medulla, what happens to the second order neuron? Anybody? It decusates, yep. Here it goes. It's going to go all the way to the opposite side. Okay, and then once it crosses over, decusates here in the medulla, it comes all the way up, and it's going to synapse with the third order neuron in the thalamus. So here's your third order neuron. Resides in the thalamus. Okay, and from there it's the same as STT, where you just, third order neuron sends out axons and conveys information about fine touch, vibration, and proprioception to the somatosensory cortex. Again, somatosensory information coming in is a 3-neuron system. And think about that. I mean, so if somebody's considered a really, really tall person and you're getting proprioception information all the way from the tip of their big toe, that's one neuron coming all the way into the spinal cord and then going straight all the way up to the medulla. 6'5" individual. That's a big old axon, right? So very, very large. Okay. Questions about either STT or DCML? STT carries crude touch, pain, temperature, comes in, that first order neuron comes in, synapses right away in, it's called the dorsal great horn. We'll get to that in a minute. And then second order neuron decusates, goes up to the level of thalamus. Third order neuron goes to the somatosensory cortex. DCML, a little bit different. That information just come right in. It doesn't do anything, but just goes straight on up. Okay, goes straight on up to the level of the medulla. Second order neuron decusates and then goes up to the thalamus. Okay, moving on then to, so this is the somatosensory information. I'm going to put the motor information on this side, just because it's kind of crowded over here. So this will be the motor cortex. Okay, so starting on this side. It happens on this side too, but I'm just going to separate out the two of them. Okay, as far as motor information is concerned, my neuronal cell body here resides here up in the primary motor cortex. It's going to be neuronal cell body. We've seen that before. And what happens is there's an axon that comes out of that neuronal cell body that's going to travel straight down through the brainstem to the level of the really caudal medulla. We'll come over to here. Okay. Once it gets there, the same axon is going to decussate. Okay, decussates at the level of the medulla, and then travels all the way down to the appropriate spinal level, and then synapses in the ventral great horn with a neuronal cell body. And that neuronal cell body, thank you. Neuronal cell body goes out and innervates skeletal muscles. Okay, so we talked about the somatosensory being a 3-neuron system and motor a 2-neuron system. With somatosensory, you have first, second, and third order neurons. With motor, it's called something different. The first neuron that's coming out of the motor cortex, this is known as an upper motor neuron. Okay? So you have your upper motor neuron, all the way from your primary motor cortex, comes down to the level medulla, decussates, and comes all the way down to the appropriate level in the spinal cord. And that synapses with a, this is an alpha motor neuron. So this is your lower motor neuron. Okay, this, either the upper motor neuron or the lower motor neuron are going to have different characteristics that we're going to talk about later on in the semester. But for now, you should know that motor information, 2-neuron system. On the top, all the way down, decussates, synapses here, with the lower motor neuron nucleus. Questions? Hopefully it's pretty straightforward. Kind of looking at these things, the only thing you can see from the front view that you couldn't see from the side view is the decussation happening. Okay, but as before, you know that injury on the left side of the motor cortex is going to affect the right side of the body. And that's how that happens. Okay, let's go ahead and move on. Okay, we'll start this one. Spinal cord, gray and white matter. Did you have a question, Jana, Tyler, or I can help you with something? You got it? I don't mind it. You can ask. I don't mind.
Just labeling.
Labeling? Was it unclear? Sometimes my handwriting isn't the best, so yeah, feel free. Yeah. Thank you. I appreciate that, Tyler. You're a good supportive guy. Okay, moving on. This is going to be spinal cord, gray, and white matter. Okay, lots of information here. All right. What I'm going to do is I'll just get started labeling a few things. And what I've tried to do is this is supposed to represent the spinal cord. Okay. What I've done is I've cut out just under this section. I've cut out a piece of the spinal cord so that you can see there's a hole there, and then I'm looking at the bottom portion of the spinal cord. So this is like a few levels down. Okay. Just trying to give it some three-dimensionality here. You can see that's just the spinal cord as like a column. Does everybody see that? Okay, looking at, I don't know if I have a pencil. That's okay, I can use this. So we talked before about gray matter versus white matter in the spinal cord. Does anybody remember where the gray matter is? Yeah, these things here, right? All this would represent gray matter. No, I'm just doing it on both sides. It's kind of hard, you know. And we can get a little bit more specific. You know, if you have a pencil, you can use your pencil. Or I'm just choosing to use gray right now. And then now we're going to start talking about sides of the spinal cord. Okay. So you have a little invagination up here. Okay. So it's on both of them, there and there. Okay, this is just a little invagination. It's a kind of sulcus. It's a kind of sulcus, and it's in the middle, and it's also in the back. So it's called your posterior median sulcus. Okay, it's just a sulcus. It's a small invagination, just kind of like the precentral sulcus. Okay, and it's in the back. Okay, if I tell you it's in the back, and you're talking about the spinal cord, is that dorsal or ventral? Dorsal, right. So that means that this part of the spinal cord back here, this backside, this is going to be dorsal. Okay, which makes the front part of the spinal cord, this is going to be ventral. Okay, dorsal and ventral. And I also know that because if I'm looking at the gray matter, you see how this more dorsal portion of the gray matter actually touches the outside of the spinal cord here? Okay, this is called your dorsal gray horn. Okay, that's going to be responsible for receiving somatosensory information. And so the word, now you can see it, so that's your dorsal gray horn there. And if this is your dorsal gray horn, the part that actually touches, and both are the same. Okay, dorsal gray horn here and here. Down here, what do you think that this part that doesn't touch might be called? There you go, this is your ventral gray horn. Okay, dorsal gray horn and ventral gray horn. Dorsal is more ventral. You can tell it's dorsal because it's actually touching the outsides. And we have the ventral gray horn not quite touching. And I labeled this as the posterior median sulcus. That's the way you know, it's another way you know it's dorsal. Okay, there's another invagination right here. So this is a big one. Okay, since it's a big opening, it's called your anterior median fissure, F-I-S-S-U-R-E. So your posterior median sulcus and anterior median fissure. It's so big, it's a fissure, not just a little sulcus. Okay, anterior goes with ventral and dorsal goes with posterior in the spinal cord. Make sense? Yes, Lauren.
You said that the dorsal gray horn was in somatosensory. That was the ventral gray horn also.
The ventral gray horn is going to house the neuronal cell bodies for lower motor neurons. We'll get there. Good question. Anybody else? We're going to talk about reflexes today and look at some different kinds of neurons in those different areas. Does that make sense? So dorsal gray horn has neuronal cell bodies for the SCT, second order neurons, lots of different kinds. And then the ventral gray horn is going to house they're called alpha motor neurons, other neuronal cell bodies for lower motor neurons. Okay, go ahead and take a 10-minute break.